Good morning, I'm Michele Esposito. My presentation is about the characterization and reliability of gallium nitride amps for high power and high temperature applications. My talk will focus on the standard LGAN-GaN amps structure and its fabrication process, on the measurement methods employed, and the innovative technologies under investigation. This is a standard LGAN-GaN high electron mobility transistor structure. This is a field effect transistor, and it's very similar in behavior with a depletion MOSFET. The very advantage of this structure is on the formation of an high mobility two-dimensional electron gas as conductive channel controlled by a Schottky junction. The conductive channel is at the aluminum gallium nitride interface toward the gallium nitride buffer. So in this zone there is no need of doping spaces, and then the conductive channel don't suffer on degradation of mobility due to impurity scattering. The fabrication process starts with the ohmic contacts formation by evaporating titanium, aluminum, nickel, and gold, and then annealing at 850 degrees centigrade for 30 seconds. The device isolation is obtained by an inductive coupled plasma etching based on chlorine gas, and the Schottky contacts consist of evaporation of nickel and gold on the algan surface. The passivation consists of silicon nitride deposition on the active region and thickening of both ohmic and Schottky contacts will improve the electrical contact. This photograph is a completed device with a focus on the channel. The characterization method employed to evaluate the RF performances is a load pull setup system at 2 GHz, and the performance obtained is a saturated output power of more or less 3 watts per millimeter with a peak power added efficiency of about 39%. So to improve the RF performances, a first order analysis on the FT and Fmax figures of merit suggests us to reduce the gate length dimension. So why to reduce this dimension? Several innovative technologies are under investigation, and the most promising of which seems to be a submicron molybdenum gate technology. The way to realize a submicron gate is to use, the best way is to use an electron beam lithography which has a resolution limit less than 0.1 micrometer. So working the realized devices have a gate length of 1.1 micrometer. So using the optical contact lithography, we are just working toward the resolution limit. An alternative way is a realization of a T-shaped gate using a molybdenum layer, then evaporating the gate metals, and so etching the molybdenum layer. Two different ways for etching the molybdenum are a dry etching and a wet etching. The dry etching consists of a reactive ion etching using chlorine-based or fluorine-based gases, but obtain low selectivity in etched materials and a contamination of evaporated gate metals. So we cannot be used. We are using a wet etching that consists of a dip in hydrogen peroxide, H2O2, which guarantee a high selectivity on the etched materials and is very gentle with the evaporated metals and on the active zone on semiconductor surface. So it's process compatible. In these two pictures, I show two different times of dip in H2O2 on 19 minutes and 29 minutes. We have calculated an etching rate of about 1 nanometer per second, so the process is very controllable. In conclusion, as future work, we will fabricate a complete molybdenum gate EMT, and we will conduct test parameter measurements to evaluate the FT and Fmax figures of merit. We are studying other innovative technologies, and at the same time, we are improving a standard fabrication process. This work is supported by il Ministero dell'Università e della Ricerca under the FIRB project, with scientific responsible Chini Alessandro. Thank you for your attention. Any question? Thank you.